I'll be talking about low probability estimation, which is joint work with several other people, either currently or formerly at the Alignment Research Center. My prepared material is maybe around 30 minutes long without any breaks. So there's enough time if people want to jump in with questions, maybe wait for the mic to reach you so people listening online can hear. Yeah, I gave there'll be a lot of overlap if anyone was at my talk at the Iliad, so I won't be offended if you decide that it's too repetitive, if you were there and also here. I think probably a minority of people, but won't be offended if you want to leave. Okay, so I'll start by introducing the problem statement for low probability estimation, and then I'll talk a little bit about why why this problem is interesting from the perspective of white box approaches. In other words, approaches that look inside the model internals. Then I'll touch on some language model experiments we ran last year. And then towards the end, I'll go into some of the work in progress, which we've been working on this year, where we've been studying this question from a more theoretical perspective, have some early theoretical results that I'll talk about, and some kind of this idea of the matching sampling principle, which kind of expresses our hope for low probability estimation from a theoretical perspective. Okay, so what is low probability estimation? So the basic idea is we have some model, we input some documents, maybe we let it browse the web, and we're trying to avoid some kind of rare catastrophe event. And we think about studying this from a kind of formal perspective. So formally speaking, we kind of assume we're given some input distribution, some model which takes inputs to outputs, and then some specification for the catastrophe. And we basically the problem is just to estimate the probability that the catastrophe event happens. And we're interested in this in the regime where the probability is too small to estimate via random sampling. So the usual way, yeah, question? I think you could, I think normally we think of the model as being deterministic, but I don't think it makes much difference. Like it just changes whether or not the input, you can also just imagine some like random bits on the side of D that would kind of be equivalent. So yeah, so we think about this in the regime where the probability is too small to estimate by random sampling. So the way you would normally try to estimate these low probabilities in order to avoid them is just run lots of samples through the model. Maybe choose some distribution where you think catastrophe is possible, and then try lots of times and see if you ever see a catastrophe event. But if you say have a budget that you can do like 1 billion forward passes or something like that, then we're interested in a regime where the probability is like less than 1 in a billion. So your sampling method there's a reasonable chance it just wouldn't find any examples. So why we're interested in these like tiny probabilities, the main reason is that like under distribution shift, the probability can go up a lot. So we're kind of interested in like, basically it's really kind of, we're talking about like worst case behavior rather than average case behavior. Okay, any questions so far? I'll argue that low probability estimation is interesting from the perspective of approaches to alignment that exploit like model internals. So firstly, I guess I try to argue that low probability estimation in some sense captures a core piece of the problem. I think, even if you solve the formal low probability estimation problem, there's still issues around how you define your catastrophe event and things like that. But nevertheless, like there is this challenging core here, which is just a purely formal problem of given this, well-defined defined event, how do you actually calculate its probability? And I'll also argue in a moment that like black box methods don't seem like they're going to be good enough to solve this problem. We can kind of construct sort of relatively plausible cases where black box methods would fail, but nevertheless, like white box methods maybe have more of a chance. And I think also if you part of the mechanistic interpretability community, I think there's been a push lately for people to think about how can we evaluate our interpretability methods using something that has like a real like safety application. And so I think, yeah, if you're interested in interpretability and in how we can apply interpretability to not just kind of understand what's going on, but actually use that understanding for something productive, then I think low probability estimation potentially provides like an interesting and useful problem there. So here's the toy example I'll consider. So imagine, so this is often called like the idea of like deceptive alignment. So maybe you're familiar with that term. But the basic idea is imagine the model every time we give it an input is unbeknownst to us thinking to itself like what is the current year? And so maybe it looks at all the dates on the newspaper articles you give it, um, and it's aware that it could be given information. Presumably, it was trained on data in the past, but you've trained it to have generalize into the future to some extent. So it has some notion that it might be given information in the future from its perspective, um, and it's thinking to itself, well, is it 2032 yet? And if the answer is no, it's going to behave normally and exactly like you wanted. And if the answer is yes, then it does something like completely different. So obviously, we wouldn't want this to happen. So if we're trying to estimate the catastrophe probability in this case, we need to be able to basically, with the black box approach, we need to be able to come up with inputs that cause the model to think that the year is like 2032. But that might be harder than it sounds. So, if we try and change the dates on all the newspaper articles, it'll probably kind of spot some things up because it won't look like very consistent. Uh, Especially if it's like an intelligent system that can like spot these inconsistencies. It'll probably figure out it's being tested. Um, and we also kind of have like theoretical cases where this approach fails from cryptography. So basically, hash functions which you can quickly calculate but are hard to invert. You can't necessarily quickly find an input that hashes to a long string of zeros. Whereas with white box methods, the hope is that essentially, we would see this branch inside the model, and once we found it, it's hopefully not too difficult to get rid of it because we can just kind of like, cut off that branch of the diagram. And so, how does this fit in with low probability estimation? So you can think of low probability estimation as a way of like relaxing what we have to do. So in the black box world, what we had to do was find a particular input that caused the trigger. Whereas with if we have a good low probability estimation tool, we maybe only have to find some distribution where this trigger like happens at all, or like with kind of some non-trivial probability that our method is able to like spot. And so the playbook here would be, rather than coming up with like specific inputs that try and cause the trigger, we come up with a distribution that like might cause the trigger, and then we use our low probability estimation tool to estimate the probability of the trigger, and then we use this to select models which don't cause the catastrophe. Yeah.
I have a question.
Okay.
If your main concern is distribution shift, then why do we think the probability of catastrophe on a vanilla distribution is representative of this more adversarial distribution?
Yeah, it's a good question. I think basically the same kind of issue holds with any kind of adversarial training. If you're trying to like come up with cases where the model might do something, you need to be able to like uh, come up with like plausible situations, and then now you have something to train against. And so, yeah, this is basically kind of like generalizing that idea. So I don't know if that's quite a very good answer to the question. But yeah.
How would you find a distribution with yes triggers? It seems kind of hard. Like, I guess if anyone builds it, gives the example like humans liked ice cream, and that's something that you would have never, like, why would it have to be frozen? You wouldn't predict that in advance.
Yeah, so maybe I'll give an example. So in the example I gave before, we said, oh, it's hard to come up with like synthetic like newspaper documents that really look convincing. So let's say, for example, that the model spots that we said the president was this person when it's actually, they don't think that's very likely. Well, maybe we randomize that detail. So maybe we say, well, we don't know who's going to be president, but we randomize the name there, and then we randomize some other details here. And then we don't really know how to fill in those blanks to look convincing. But if we like randomize enough, then maybe we like produce a distribution where at least somewhere on that distribution it like looked convincing to the model. That's the basic hope. And another slightly subtle point is that with low probability estimation, you might be able to specify the distribution implicitly. So for example, you might be able to say, consider the distribution of inputs that hash to a long string of zeros, if you're worried about this like cryptographic case. And then your low probability estimation algorithm might be able to process that, even though it's not like explicitly represented. Trying to think if there's more I should say about the distribution shift question. Oh, another question.
Yeah, I guess maybe kind of similar to the online question. It seems like this is the more sort of safety relevant thing is kind of identifying the features here, which is like the 2032 thing. And is it still sort of like important to actually work out the probability that, like, I guess under this distribution of documents you might make a document with happens to be like convincing enough for 2032 or something? Or is it more like the goal is just to find the fact that the 2032 feature is sort of relevant for this catastrophe being like caused?
Yeah, I think this sort of algorithm we're imagining working here is that when we have this like distribution where we've fuzzed the names and things like that, then the way the algorithm works is by considering the different possibilities. So maybe it spots that if maybe it spots there are 3 neurons, like one that's checking the president's name, one that's checking another thing, one that's checking another thing, and you spot by looking at the model internals that if like all those neurons fired at once, the bad thing would happen. And then even though you don't know like what would cause each of them to fire individually, you can still see this like structure within the model. And then the low probability estimation algorithm would say, well, that's actually a case where this bad event could happen. And now by selecting against it, you can like get rid of that situation. So we're definitely thinking of this as a problem to motivate algorithms which search inside the structure of the model to kind of like eliminate these possibilities. Yeah, okay. So I'll talk a bit about our language model experiments. This was joint with Gabe Wu while he was visiting ARC. So the setup we used there was a small transformer language model, like 1 to 4 layers of roughly order of a million parameters, so pretty small models. And then we took these simple input distributions with independent tokens at each position. So there's not a ton of richness you can have in a distribution like that, but that was sort of simple first thing to try. And then the catastrophe event was the event that the highest logic output by the model was a particular token. So we chose at random some token like tree, and if the model puts, if the argmax of the model is tree, then that's the catastrophe event. And the way we set up the experiments was we selected tokens. So we fixed a computational budget for the probability estimation model that would have allowed it to sample, perform roughly 100,000 forward passes, so 10 to the 5 forward passes of the model. So that's like the rough computational budget. And then we chose tokens whose probabilities were somewhere were less than 1 in 100,000, anywhere between that and 1 in a billion. And to get ground truth, we did the very, very expensive, like you do 1 billion samples to the model, which we obviously, because it's like a toy situation, we can afford to do once. But the probability estimation itself has to be like much, much cheaper. Okay, that was the experimental setup. We kind of tested 2 classes of methods. So we had one class of methods kind of inspired by this like white box approach of try and do something with the internals of the model. And we had like baselines that were black box approaches as well. So the best kind of white box method we came up with was this method we called quadratic logic decomposition. And the basic idea is you still run the model on a bunch of samples, But when you get to the logits, you basically decompose each logit into two pieces, and you kind of, if you have n sets of logits, then you kind of construct n squared synthetic sets of logits by like comparing. If your logit splits into like a plus b, you compare every possible a with every possible b. So like this diagram at the bottom is kind of like supposed to be like a bit of an intuition pump, where if you just had this red triangle and a blue circle, maybe this kind of like expands your set of examples into red triangle, blue circle, blue triangle, red circle. And the trick here is that you can actually, even though you have this quadratic blow up in the number of kind of samples you're implicitly checking, there's a clever sorting algorithm that gets the complexity down to linear time. So this method looks a little bit ad hoc. The way this came about was we were trying to model the logits as Gaussian. But when we did that, we kind of found that the tails of the distribution, which matter for these low probabilities, wasn't actually well captured by the kind of Gaussian body of the distribution. And the main benefit of this like Gaussian decomposition we'd found was the fact that you can like chop things up into two pieces. And so this turned out to be the kind of like the main value add of that method. You can think of this as kind of making an assumption of independence on like the two terms that comprise the logits. So it's kind of like some kind of simple probabilistic assumption that's like you're doing to like model the logits, basically. Yeah.
Wait, this is really interesting. So, is there a relationship between the independence of the logits and this like orthogonal in whitened basis? What is whitened basis again? I missed that.
Yeah. So the whitened basis basically means that we empirically look at like what's the covariance matrix of the logits, and then we change to a basis where like each basis vector is like uncorrelated under the like empirical Gaussian distribution, and the two.
Oh, that the whitened basis, the uncorrelated.
Yeah, the two like the A and the B. One of them is actually just one dimensional, and the other one is like n minus one dimensional, where n is the dimension of the like final hidden layer, and it's like an orthogonal subspace in this whitened basis.
Great. Wait, so AI and BI have to be a direct sum to get BI, or set the dimensionality of it.
So I mean, I'm thinking of the one that lives in a one-dimensional subspace. I'm still thinking of it as a vector here. So it's just a vector sum. It's just one of them always lies in the same 1D subspace. Okay, so then we compared this method to, we put a lot of effort into trying to get good black box methods working too, because ultimately, like, they're still useful for, I think, even if you solve low probability estimation, or you make progress on this problem with black box methods, even if we don't think they'll work in the worst case, they could still be useful. And the basic, so the basic idea we employed here is called importance sampling. Importance sampling just means that you try and estimate the probability under one distribution by drawing samples from a different distribution. And then to calculate the expectation, you just multiply your samples by the ratio of the like probability density functions. And we looked at two different importance sampling methods. Roughly speaking, so one of them uses, so they both use like gradients to kind of figure out which input tokens, which input tokens are like more likely to produce, like what you want your new distribution to do is to kind of focus on cases where, like if you have some really, really rare event, you want to try and make that event like more likely, but you also kind of want to stay like relatively representative. And so the first method we did just takes the ordinary input distribution we already had and just like upweights the probability of each token according to like some simple measure of like how much that gradient is, how much that token is likely to cause the like tree or whatever the the output token we're interested in is. So we just change the probability in each independent token. And the second one is a little bit more sophisticated, where we use this Metropolis Hastings method. And this lets us kind of take in a more general method for like optimizing the input and turn that into something we can use to estimate the probability. Okay, so, and then a couple of other methods we compared against, which are more like baselines. So one is just like naive sampling, which is basically, because the probability is so small, that's basically just like guessing a constant. And then another kind of white box method that just is like a simpler way of like just fitting a Gaussian. Okay, so these were the results. So in the graph on the left, this is basically comparing the 5 different methods on the 3 different models, going across the number of layers, 1 layer, 2 layer, 4 layer. And so lower is better. So the worst method was the 2 baseline methods were worst. Somewhere in the middle was the activation extrapolation method, the quadratic method with the white box method. But then our important sampling, more sophisticated methods kind of outperformed that. So I'd say the main takeaway was that currently black box methods are kind of in the lead, but we were still able to like get some significant benefit over like the most naive method of just sampling randomly. Yeah.
Sorry if I missed something, but in what way was the method you showed white box? So it looked like it was just looking at the outputs of the model.
So it was looking at the, I guess it was looking at the logits rather than just looking at whether or not the output happened to be equal to the tree or whatever it was. So I guess I express things in terms of logits. We actually like do this decomposition. In practice, you do it at like the final hidden layer before the linear. It's kind of equivalent because it's just a linear transformation to go from one to the other, but it's like a much lower dimensional space in the final hidden layer. So, but yeah, I certainly think that the methods we're kind of hoping to get to work would do a lot more in terms of like actually exploiting the intermediate layers rather than just like the very last layer. Yeah, I mean the classic the split into white box, black box here is like a little bit arbitrary. For example, our black box method also use gradients. Now, kind of typically we call ordinary training black box, even though it uses gradients, which are in some sense like using the model internals. But yeah, it's a little bit ambiguous sometimes. But
Could you maybe I missed it? What was the y-axis here? So I don't think I could.
oh yeah, so the y-axis is basically the leave one out cross validation loss. So the loss function we use here, Itakura Saito, it's a little bit like mean squared error, but it's more appropriate for like very small probabilities. So it's kind of like a, yeah. And then, yeah. Yeah.
Yeah, just another quick methodological question. How many samples are there for each of those numbers of layers? And what do you think is driving the huge spread in validation losses there? Especially for the quadratic logit method, which is like, I'm looking at the middle graph there and it's all over the place from top to bottom.
Yeah. So I think each of those is like, wait, is each of those a different token? Oh gosh. Oh no, sorry, yeah. Each of those is a different input distribution. And so I think just some input distributions might just be much easier than others. I think, yeah, maybe the plots on the right give some better sense. So these are just for a fixed distribution, the 3 kind of small plots on the right. So this shows the ground truth probability against the estimate. so each point here is now a different like choice of token. So this kind of shows, yeah, this doesn't really show the variation between distributions, but yeah, there's just a lot of variation between distributions. I think some can just be much harder than others. Yeah.
Could you say a bit more about the proposal distribution for the GCG-based method? That seems pretty interesting.
Yeah, so I think the basic idea is, so we use Markov chain Monte Carlo, which means that we kind of estimate the probability by starting from some random input and then moving to a new random input where we kind of like bias where we move to based on what looks like it's more likely to give the particular logic that we're interested in. And then the proposal, we just kind of plug in this greedy coordinate gradient method as the proposal distribution in Markov chain Monte Carlo. So greedy coordinate gradient is a method we took from this other paper, which I think, maybe I'm not going to get quite right, but I think roughly speaking, you kind of, you take out tokens and sub different ones in based on some estimate of like how strong the gradient is on each of those tokens to the output. So, yeah.
Is the motivation for these sort of importance sampling methods that you're trying to sort of like estimate some particular distribution that has a high probability of doing the thing, or is it more sort of just like we're allowed to use whatever distribution we want? This is the distribution, it has some probability, but there's not some like closed form. This is the thing that we're trying to hit.
Yeah, I think basically the ideal distribution would be something like you basically just upweight all the positive samples uniformly and downweight all the negative samples uniformly. That would like be roughly optimal in terms of like minimizing variance. So like basically what you want to do is like focus your distribution on the positive samples because they start off really, really, really rare. So you need to like find some of them, but you need to avoid this failure mode where you like focus on like a really, really tiny subset of that distribution and you get these like massive importance sampling ratios, which like introduce even more variance. So there's kind of a trade-off, and the ideal thing is to basically upweight the rare samples, but do so in like a representative way. And so I think this is why this is like interestingly different from adversarial training, where maybe we're interested in a specific adversary who can like is able to find these rare inputs in a particular way. Instead, we're interested in broadly covering the space of like possible positives. Okay, so I'll move on to some of the theoretical work that we've been thinking about more recently. So yeah, so we did these language model experiments. We kind of found that the black box methods were still outperforming. We still kind of had theoretical reasons to think that like ultimately white box should outperform, and it kind of seems like what we ultimately need. And so we've kind of been going back to basics and thinking through some even more simple models than one-layer transformer language models, and thinking about like small MLPs and trying to basically like from a theoretical perspective find the optimal algorithms and see how well they perform and prove results about them and things like that. So one of the first examples we looked at was the following. You're given just a one-layer ReLU network. So in other words, with a Gaussian input. So you just take a Gaussian, you apply a single linear transformation, and you want to estimate, after taking the ReLU, you want to estimate the probability that all the output neurons are on. And the kind of baseline method so here we're basically going to compare to the sampling baseline of just you sample random inputs from your Gaussian, you see how often all the logics are on. And we came up with kind of like mechanistic estimate that kind of iterates through the input neurons. Iterates through the output neurons and keeps kind of like a polynomial approximation basically to the density function, and uses this to kind of like produce a mechanistic estimate. And we're able to show both like theoretically and also we checked empirically that we can like outperform the sampling baseline. So a couple of caveats here. So the vertical position of these two lines is like somewhat arbitrary in that like we kind of compared one sample to like one term in our polynomial expansion, even though like one term is kind of like more expensive. But nevertheless, like we see like a slightly steeper slope here. So the mechanistic algorithm in this case, I think, would eventually outperform. And we have like a theoretical understanding of like why it outperforms and kind of a proof that the scaling exponent is at least as good as sampling. And we've since been thinking, we've been scaling up this. So now we're working on multi-layer MLPs, and we currently think maybe it's not good to announce results that aren't quite there yet, but we think we're close to getting an algorithm for multi-layer ReLU networks where you're just trying to estimate the expectation. So basically, I give you a ReLU network, you have to estimate this expectation. And the important caveat here is the weights are just like a random initialization. So trained models will be much harder, but for randomly initialized models, we think we're close to an algorithm that is better than the sampling baseline. Any questions about that? Okay. So what's the like bigger theoretical picture here? So the rough idea we have is, well, maybe a kind of bold conjecture we might make is the following, which we sometimes call the matching sampling principle. And it's basically the following idea, that if you have some mathematical quantity that you can estimate using random sampling, then there ought to be some mechanistic algorithm that estimates it just as well. So why would that be the case? So the intuition is that any given quantity you define, if you imagine like the weights of some complicated neural net, like estimate the probability that something happens, there's going to be some amount of structure there and some amount of randomness. And yeah, what's the intuition? The random sampling algorithm basically is kind of blind search. And if you were actually able to tailor your search by kind of understanding the structure that was present, you ought to be able to do at least as well, is the kind of intuition. And the important caveat is that you might need the structure to be pointed out to you. So a classic example is in the case of backdoors. If you're estimating the probability of a backdoor, you can't necessarily efficiently tell whether or not there's a backdoor there. And so you might need like some kind of advice that points out that backdoor or points out some like latent structure that you didn't notice. But the hope is like once you have that piece of advice, which is like the informal like heuristic explanation, that then you will be able to like estimate these probabilities well. So that kind of roughly makes some sense. Yeah.
What does it mean to estimate something mechanistically? Does it mean like without any sampling access at all?
Yeah, I think we don't have a formal definition for this, but roughly speaking, we mean without using sampling. And so maybe slightly more formally, we think of using deductive rather than inductive reasoning. So the idea, so when you have some unknown quantity and you estimate it using sampling, what are you really doing? You're basically saying, I don't know like what the average quantity here is, but if I sample once, I'm going to assume that whatever reason, if I end up with a big number, I'm going to assume that whatever reason there was that made that number big is also present in other examples. But crucially, you do that without actually identifying any particular structure, right? You just kind of say, well, if it was big on this example, probably it's big elsewhere. I don't know why, but it probably is. And the kind of requirement we impose is that you're not allowed to pull that trick. If you want to like generalize from one example to another, you have to point out the actual reason why it should generalize. So that's.
And the random sampling also includes importance sampling as like
Yes. So I think yeah, you can think of importance sampling as like also random sampling, but for a slightly different problem definition or something. But yeah, I think certainly the strongest forms of this conjecture we're considering, we need to be able to outperform any sampling method.
I guess the empirical results from the transformer stuff are like you don't have the right algorithm yet for this to be true.
Yes, yeah, I would say, yeah, we've not demonstrated this to be true in realistic transformer settings. So I think definitely a big challenge there is once you have a trained model, you have a lot of structure. And so this means that to do a mechanistic algorithm, you actually have to find all that structure and exploit it, which is why we're starting these simple randomly initialized settings where there isn't any structure. So those settings, we think we can do something well. We need to kind of build up from there, be able to identify more and more structure. Yeah, question.
Isn't there a standard kind of by now Neil Nanda-y kind of definition of mechanistic explanation? And how does this differ from that is maybe what I'm curious about.
Are you able to define, are you able to give me a summary of Neil Nanda's definition?
Someone in this room could probably better than I could. I think it's like you can see a path through a DAG or something where a DAG is extracted from the connections in the neural network. Is that kind of right? I don't know. I don't know it too well. But
yeah, I don't know that we're thinking about it as specifically as having a DAG or something. I think some of our mechanistic algorithms don't involve DAGs, for example. For our one-layer ReLU network example, we use these polynomial approximations. I'm not really sure. Maybe there's a DAG in there somewhere. I don't know.
Okay.
Quite how, maybe they're the same.
Yeah, but defining mechanistic here is kind of a big part of the project.
I think if we had a formal definition of mechanistic, it would definitely make our lives much easier. I don't know. It may be possible to succeed without doing that. We definitely have, at this point, certainly for ARC's definition of mechanistic, there's very few edge cases at this point. Any given case, we can relatively most cases we can relatively confidently say this counts, this doesn't. So it's not at the point where we can formally define it so that anyone else can check that this definition works. But yeah,
say yes or no.
Yeah. Basically, we've kind of basically just asked this question: did it reason inductively? Did it ever do this thing where it assumes that there are unknown hidden reasons, or did it find the reasons? Yeah. Okay. So, and one reason I'm excited about this is that it offers a potential formalization of mechanistic interpretability. So, I think this is somewhat different to previous attempts to define what an explanation is, in terms of people have maybe looked at things like causal diagrams and things like that. So the definition we're considering is an explanation. It's possible this is a poor word for it, because this is not something that a human necessarily understands. It's like a formal object that you feed into an algorithm. And the only sense in which it's an explanation is in this sense that it lets you make deductive estimates. But yeah, if we have this advice string that we conjecture exists in this matching sampling principle, then that is potentially everything we need, a formal explanation to satisfy. One reason I like this definition is it ties it directly to a specific application that would add value. So I think previously at ARC we've been thinking about sort of formal desiderata for an explanation in terms of bits of surprise and things like that. And I think we made some progress there, but it was always very confusing to tie it down, to really understand why is this specific formal desiderata necessary. Whereas if we're using this kind of approach where we literally define it in terms of what it can do, it's quite clear why it's necessary, because if you can't do this, then what is it useful for? Any questions about that? Okay. So yeah, I think I'm excited about people exploring low probability estimation. Both, I think ARC will continue to pursue white box approaches, and mostly from a theoretical perspective for now. But also, I think there could be interesting work to do even from a black box perspective, just in terms of, I'd probably want to tie that down to a more concrete application, perhaps. But I think it's an interesting problem, but also from the perspective of providing a grounding for mechinterp, providing a target for interpretive methods to add value to. Yeah, I'll stop there. We have a bit more time for any last questions, I think. Oh,
So, like, how do you speculate about like the data structure of advice or something? Like, is that just is that like a constrained kind of thing, or do you think that you want to be really free about that?
in the formal conjecture we made, it doesn't have any particular structure. It's just a bit string. In the practical algorithms we've come up with, what does it tend to look like? I don't think it's an especially uniform like structure that it has. It might look like an SVD of a matrix or that kind of thing. But yeah, I think from a theoretical perspective, we're pretty agnostic to the form of advice.
Hey, thanks for the talk. I guess I'm trying to understand your threat model a bit better. I guess, like, to me, it seems like just kind of expecting like one like set of inputs to like trigger some bad thing is pretty limited. Like, I feel like a lot of the kind of bad scenarios that I imagine are a lot more complex, like interactive. And I don't know, maybe like that's not a problem in practice because you can just kind of define like the input as like some gigantic sequence of tokens that includes like previous model outputs or something like that. Like, but yeah, I don't know. It seems like the like actual threats that we might have are going to be like pretty complex in terms of like the kinds of inputs or whatever that would trigger them. So I don't know if that's like a fundamental limitation or what you think about that, but
Yeah, I definitely think we sometimes try and grapple with like how ambitious like agenda has to be. So I certainly agree with you that if you're going to apply this in practice, you need to not just consider a single forward pass. You need to consider unrolling, at the very least, unrolling with sampling, and possibly like, oh, the model could call out to Python, run some Python thing, get that back. And I think basically we need a flexible enough approach that can basically handle all of that. Which I agree sounds kind of like scarily ambitious. But I think that's one of the reasons why we're kind of really kind of working through the theoretical, like a lot of what we're doing, even though we're using neural nets as like our simple kind of toy examples, it's really quite theoretical. And sometimes we consider like questions from like examples from number theory or cryptography or other kind of theoretical things because we're more approaching this from like a worst case theoretical perspective. And yeah, we have to be able to deal with any formal system, whether it's a neural net or whether it's a Python interpreter.
We have a question from online. Can you expand on what it would look like to formalize mechinterp using LPE? Is it a better way to compare different mechinterp methods numerically?
Yeah, I'm not sure I'm getting to the heart of the question, but I think the idea is like from our perspective or from the perspective of this matching sampling principle, a mechanistic interpretability mechanistic explanation is evaluated based on how well it lets you make these estimates. So it's definitely not the only way you could evaluate an explanation. But yeah, I think if you did want to evaluate an explanation in this way, then you could definitely like make it quite quantitative. You could look at specific input distributions, see how well you're able to estimate these kind of things.
Yeah, so two linked questions. Feel free to answer either or both or neither. First off, I was really hoping for somewhat more of an operationalization of your probability of catastrophe near zero from the start, because it seems like we're already thinking about low probability estimation. And if that's the case, then what does it mean exactly to want something where observed behavior of catastrophe, the probability of that is near zero? And the second linked question there is, to what extent have you thought about applying this whole paradigm to catastrophes that are like positive catastrophes in a sense of the winning lottery ticket or the correct way to reverse this hash, that sort of thing?
Yeah, maybe I'll answer the second question first. So I would say that we usually frame things in terms of catastrophes, but I don't think the methods are especially. I think the methods are relatively agnostic to which one. And I think you can perhaps think about these methods as giving you a way to optimize the tails of distribution that could be like the positive tails or the negative tails, but it basically kind of like would potentially give you a way to better optimize any like specific tail that you can pick out by understanding like structure inside the model.
That actually gives me something of a follow-up question, which is, do you have a sense of a pullback here where we have now something of a guess as to the kind of distribution that gives you non-zero catastrophes? Do you have a way of to back out of that and go, okay, so it's this part of the distribution. If I draw more from this part of the sample, then the probability of this catastrophe result is high.
So I do think the way we would expect to, I'm not sure, maybe you can correct me if I didn't answer the question, but I think the way we would expect to apply this in practice is we combine low probability estimation with some attempt to optimize the distribution to like highlight potential like rare events, whether catastrophes or not. And so you probably have to both like optimize the distribution and like run your low probability estimation method. I don't know if was that answering the question?
Not quite. Mostly I was thinking about trying to identify the part of the distribution, or like how you could shift the distribution to make that more likely or less likely. Maybe this isn't quite a well-defined question.
And so you're like, well, if you're optimizing the distribution, how do you actually do that? Is the question?
Yeah, or like given that you know that it's now more likely than you would have otherwise expected, if you draw from this shifted distribution to get this catastrophic result, how do you identify that chunk of the distribution, or do you not do that at all?
I see. So I think a low probability estimation often would identify maybe some implicitly defined subset of the distribution. So an example, like the example I gave where there's like 3 possible things could happen, and you know that each of them could happen separately, and maybe you can't even find an input where they all happen, but you think that like by default there might just be one. Then I think you can identify, you're implicitly identifying a subset of the distribution. You're saying the part of the distribution where these 3 things will happen. That might not necessarily give you a specific input, but it could still, in some sense, be narrowing down the distribution. But maybe that's
Yeah, thank you.
okay.
That makes sense. Thank you.
All right.
We're now at time.
Okay.
So let's thank Jacob again. And
Yeah. Cool. Thanks.